In the previous chapter, it was shown that the expressions that represent the starting point of the hyperbolic theory of relativity are, in origin, an internal view of an axis rotation. Such an internal view involved the introduction of the imaginary unit, and this made the final product, that is, the Lorentz transformations, to be different from a conventional axis rotation. However, how different are they? This is exactly what we want to see in this present video. We want to see the difference between the Lorentz transformations and a change of coordinates due to an axis rotation. To do so, one needs to follow the same procedure that led to the Lorentz transformations, but now we're starting from the conventional rotation of axes without the introduction of the imaginary unit. Thus, we first consider a particular rotation, the one that rotates the x-axis to place it on the point in question, and then we define a velocity v sub g. Next, the cosine and the sine need to be isolated as a function of v sub g. Finally, one needs to substitute these expressions in the axis rotation transformation. Proceeding in this way, one encounters the expressions of an axis rotation transformation, but now expressed as a function of v sub g. Let us now compare this result with the Lorentz transformations. As for the first expression is concerned, the one referring to the x prime, there is a sign change in both the numerator and in the square root of the denominator. In contrast, in the second expression, which refers to the t prime, there is only one sign change, and it is, again, the one inside the square root. Therefore, it is clear that the conventional axis rotation is not exactly the same as the Lorentz transformations. However, a closer look reveals that they do not differ too much. The square roots act as a scale factor, so the sign change in them is not too significant. The one that is important is the one in the numerator of the first expression, which affects the time variable. Therefore, although the Lorentz transformations are not identically an axis rotation, they are very similar in the sense that they only differ, for practical purposes, in just one sign. Having said that, it makes sense to geometrically represent as a first approximation the Lorentz transformations in terms of an axis rotation. Therefore, let's do so and let's see what differences are introduced by that single sign change. Note that as the proper time of the p-point evolves, the point is seen to advance towards positive x in the S reference frame. In contrast, in the axis rotation representation, as the point evolves towards greater values of its proper time, that is, as the point p climbs up the t' axis, it is seen to advance towards negative x in the S reference frame. Obviously, this difference is due to that sign change that was detected in the numerator of the first expression, which affected the time variable. To correct this difference, one can imagine that the proper time changes its sign, that is, to imagine that it evolves in a reverse mode. In this way, as the p-point climbs down the t' axis, it moves towards positive x as expected. Let's see if, taking in mind the reverse time adjustment, the various relativistic effects can be deduced from such an axis rotation representation. From this drawing, one realizes that the geometric relation between t and t' is not affected by the inversion of the proper time. They relate with each other by means of a projection that can be expressed using the cosine of theta. And since the cosine of theta is equivalent to the Lorentz factor, one ends up finding the expression of the time dilation. Therefore, it seems to work. That is, although the Lorentz transformations are not identically an axis rotation, the axis rotation seems to provide a good geometric approximation to derive the different relativistic effects. Let's see now if the length contraction can be derived in a similar way. Suppose a bar of proper length L' at rest at the origin of the S' reference frame, which is moving to the right at a velocity v sub g with respect to the S frame. In the axis rotation representation, we see that the rear end of the bar moves on the diagonal line B, while the front part moves on the diagonal line A. Note that according to this representation, the B line intersects the vertical axis x equals 0 before the A line does. This means that according to this representation, the rear end crosses the origin of S before the front end does, which is not the physical situation set at the outset. Again, this is due to that sign change. Therefore, one needs to imagine the inversion of the proper time to make the two representations be consistent. Let the time measured from S taken by the bar to cross the origin of S be called t sub p. And let's draw the length L of the bar measured from S. From the picture we see that L and L' are related by a projection. Therefore, we can write L cosine of theta equal to L'. In this way, the formula for the contraction of length is obtained geometrically. Therefore, it works in this case too. And this is great, because we are obtaining a way to geometrically visualize the different relativistic effects, which is a powerful tool. This same expression can be deduced from the time t sub p that the bar takes to cross the origin of S. Now let us consider another situation. We have a trolley moving in a moving train car. We want to calculate the speed of the trolley when observed from the platform, that is to say, from S, if the relative speed u' between the trolley and the train is known, and also the relative speed v between the train and the platform. According to the axis rotation representation, the relative velocity between the trolley and the train is proportional to the start tangent of the theta sub 2. While the speed of the train, seen from the platform, is proportional to the start tangent of theta sub 1. Then, the speed of the trolley seen from S must be proportional to the start tangent of theta sub 1 plus theta sub 2, which after a bit of calculation ends up giving the expression of the velocity addition formula. Let's see now whether the twin paradox can be geometrically visualized too. First, we draw the axes that represent the first twin at rest in a fixed reference frame on Earth. Next, we draw a second frame which is rotated with respect to the first one and which represents the second twin in the spacecraft moving away at the speed v sub g with respect to the Earth. We now mark with a straight line the timeline of that twin inside this spacecraft. It has a length t'. When the spacecraft stops, it reverses its course and returns to Earth at the same speed. This is equivalent to a system of axes which is rotated in the opposite direction with respect to the previous ones. Let's mark the timeline of this traveling twin on his way back. Since it takes the same amount of time to go and to return, t' is equal to t double prime. And from the drawing, we see that both t' and t double prime are related to t through a projection, as it was the case in the time dilation. In this way, the amount of time spent by the traveling twin is shorter than the time spent by the twin left on Earth. Thus, our geometric method seems to work in this case too. Per tant, encara que les transformacions de Lorentz no siguin idènticament una rotació d'eixos, la rotació d'eixos segueix essent, amb l'ajuda del pedaç de la inversió temporal, una representació que ens ajuda a visualitzar sobre el pla els diferents efectes relativistes. Això és així perquè les transformacions de Lorentz són, en essència, una visió interior d'una rotació d'eixos. És a dir, tot sovint s'ha pensat que la geometria de l'espai-temps és una geometria hiperbòlica. Tanmateix, cal tenir en compte que aquesta hipèrbola resulta d'una visió interior del cercle. Amb això el que estem dient és que l'estructura de fons segueix essent el cercle i, per tant, és el mateix cercle el que acaba proporcionant la millor aproximació geomètrica a la relativitat.